Good morning, Professor Shien and fellow classmates. I'm Iris, and my partner is Shien. The primary focus of our presentation will be on UV-Vis. This is an outline of our presentation. I will first be covering the introduction and theory of UV-Vis, while Shien will be presenting on the working principles, qualitative and quantitative analysis, as well as applications of UV-Vis. Firstly, UV-Vis is an abbreviation for ultraviolet visible spectroscopy. UV-Vis utilizes light in the visible and its adjacent spectrum such as UV and near-infrared. It is an absorption or reflection spectroscopy of part of UV spectrum and the full visible light spectrum. UV-Vis is normally used as a quantitative measurement of the concentration of the absorber in the solution, which contains transition metal ions and highly conjugated organic compounds. The UV-Vis spectroscopy probes electronic transitions of molecules as they absorb light in the UV and visible regions of the EM spectrum. Now, I will be elaborating more on the theory given by the absorption of UV-Vis. At the relevant wavelength, electronic transitions occur. Electrons in their stable state are excited to higher energy state. In the case of organic molecules, electronic transitions are applicable to species with an extended system in the colorless solution of alternating double and single bond. On the other hand, for transition metal atoms, transitions are applicable to anything with color which absorbs visible light. Let me first bring the focus to transition in organic molecules. Transitions are applicable to molecules containing chromophores, which are functional groups absorbing light in UV-Vis range. The molecules absorb energy, promoting electrons to an anti-bonding orbital. Most of these absorptions involves transition of electrons from pi to pi asterisk, non-bonding to sigma asterisk, or non-bonding to pi asterisk, as other transitions require too much energy. In the case of a sigma to sigma asterisk transition, a photon absorption with a wavelength not in the UV-Vis range is required. Here are some guidelines of the wavelength absorption for some transitions. It is important to note that electronic transitions take place between various states. In case any of you are unsure of what an anti-bonding orbital is, an anti-bonding orbital possesses a different shape and energy from the bonding orbital. It is always demonstrated with the use of an asterisk after its chemical symbol. Typically, when a bonding orbital forms, it is at a lower energy than the original atom, as the molecule is more stable due to the energy released. A bonding orbital is normally stable as a result of the attraction between the nucleus and electrons. However, an anti-bonding orbital is less energetically stable than the original atom, as there are no equivalent attraction. The attractive force between the nuclei and electrons pull the two nuclei apart. There is very little chance of finding the electrons between the two nuclei in the anti-bonding orbital. Allow me to further illustrate what I mentioned previously. Take for example, we have a pi to pi asterisk transition in ethylene. We know that in ethylene, the electrons are paired in a pi bonding orbital. In UV-Vis, UV provides sufficient energy for an electron to be promoted from a pi bond to a pi asterisk bonding orbital. This pi asterisk bonding orbital now becomes the highest occupied molecular orbital, and electrons become unpaired. Now that we have covered the knowledge behind electronic transitions in organic molecules, let's move on to electronic transitions in transition metals. As many of you are aware, a transition metal is one which forms one or more stable ions which have incompletely filled the orbitals. Transition metals possess a complex formation. This complex formation consists of a complex and a ligand. A complex is a central metal ion surrounded by ligands, while a ligand is an atom, ion, or molecule which is able to donate a lone electron pair. Transition metals possess a very interesting property that organic molecules do not. Transition metals are able to change colors due to de-excitation of the orbitals. A portion of visible light is absorbed to promote the d electrons to higher energy levels. The final substance color that we observe is the complementary color of the light that is absorbed by the solution. For example, a solution will appear blue if it absorbs orange light to promote its d electrons. So why are transition metals able to change its color based on its bonding, orbital arrangement, and coordination complexes? This phenomena is explained by the ligand field theory. In free metal ions, the 5 d orbitals in transition metals possess equivalent energy levels. However, in the presence of ligands, the d orbitals will possess different energies. Ligand field splitting is dependent on the geometry of the ligand, whereas the amount of d orbital splitting depends on the type of ligands. Changing a ligand, or changing the coordination number, will alter the energy split between the d orbitals. This will change the energy difference between the two orbitals, which will also change the frequency of light absorbed into the solution. The spectrochemical series ranks ligands according to the energy difference between the orbitals in their octahedral complexes. Ligands producing a large splitting are called strong field ligands, and ligands which produce small splitting are called weak field ligands. The greater the splitting, the more energy is required to promote an electron from a lower orbital to a higher orbital. This corresponds to shorter wavelengths. Now, I'll be handing the rest of the time over to Shien, who will be elaborating on the working principles of UV-vis spectroscopy.
Thank you, Iris, for the introduction. Continuing with our presentation, we shall look at the equipment. This is a general flow of the UV-vis process. Firstly, deuterium lamp provides UV light, while tungsten lamp provides visible light. Light from both lamps will converge, and the monochromator containing the prism will separate the light into different beams with different wavelengths. After the monochromator, the beam splitter will split the beams into two different chambers. One is the reference chamber, and the other is the sample chamber. The photodiode collects the light detected for each wavelength and generates an absorbance versus wavelength graph through data processing. You may wonder, how do we relate intensity to the graph shown from the detector? The main principle of UV-vis is absorbance, which is a quantitative measurement of the extent to which a compound absorbs UV radiation at a particular wavelength. Absorbance is inversely proportional to transmittance. Transmittance is the net change in intensity, whereby the lesser the light is absorbed, the more the transmission. Since the detector only detects how much light is transmitted, we should plot the graph as transmittance against concentration, right? However, this graph will not give us much result as the graph plotted has no linearity. Now, many of us would think, what is the problem pertaining nonlinear graph here? To explain further, it is difficult to extrapolate the graph to find the unknown concentration of the solution as compared to the linear graph. In order to get a linear graph, we have to put the results through a log function to find the absorbance. However, how do we find the concentration of the unknown solution? We have to use the Beer-Lambert equation as shown here. Now that we have covered the principles of UV-vis, you'll be wondering how we should analyze the absorbance against wavelength graph. This is where we need to calibrate the graph in order to accurately find the concentration of the sample. In order to calibrate the equipment, the identity and the maximum absorption of the sample should be known. First, we have to prepare a series of standard solutions to determine the maximum wavelength. And next, measure the absorbance of all standards and maximum wavelength. The measurements must satisfy Beer-Lambert law, where the calibration curve must be a straight line. Now all you have to do is to measure the absorbance of the solution with the unknown concentration at the same wavelength. One example is to find the concentration of potassium permanganate, which is KMnO4. The equation of the slope is y equals to 1442.7x plus 0.0149. The question is, if a sample has absorbance of 0.4, what is the concentration of KMnO4 present? By substituting y equals to 0.4, S is equals to 0.270 millimole per liter. However, the relationship between absorbance and the concentration of the sample may not be linear. These are some of our reasons as to why there is no linearity. The most important point to take note is that samples should be diluted, because at high concentration, solid molecules can cause different charge distribution on their neighboring species in the solution. Since UV visible absorption is an electronic phenomenon, high concentration would possibly result in a shift in the absorption wavelength of the analyte. So, how is UV-vis applied in the real world? UV-vis is commonly used in food safety, healthcare, chemistry, material science, and manufacturing, but I'll be covering two applications in food and dye industry today. Firstly, UV-vis is applied to detect toxic contaminants in food products. One example is detecting high levels of melamine in food, as it is detrimental to both animals and humans. When melamine is detected using UVVs, the characteristic absorbance of silver nanoparticles at 395 nanometer decreased, whereas a new absorption band at 645 nanometer increased. This implies that silver nanoparticles are aggregated as melamine is detected. To examine the detection of melamine using p-nitroaniline, in short PNA, modified silver nanoparticles, control experiments were taken using melamine. As shown in the top right photo, 0.1 millimoles per liter of other molecules with similar structure did not give a change in color, or UVV's absorption spectrum of PNA modified silver nanoparticles. Secondly, UVVs is used in the quality control of the development and production of dyeing reagents and inks. Conjugated organic compounds absorb light when their pi electrons are excited to high energy states. One example is erythrocene, which is a red dye. It loses protons and gains electrons in aqueous solution. Delocalization of electrons in erythrocene causes this molecule to absorb UVVs at 424 nanometer. Green region of the spectrum enables the compound to appear red. Most simple analyses measure the absorbance one wavelength at a time. However, more chemical information is present if measurements are made at many wavelengths simultaneously. UVV's instruments capture all the light that is transmitted and split the light into different colors using a prism. Absorbance at different wavelengths is then captured on a linear array of photodiodes, which is advantageous for measuring many different molecules at the same time. These are our references. We have come to the end of our presentation. We hope that you have enjoyed our presentation on UVVs. Thank you for your attention, and you may now ask us any question you have. We will try our best to answer.